Good afternoon, everyone. Welcome back to Essential Perturbation Theory and Asymptotic Analysis. Any questions? Well, today, good news, we're going to finish chapter 4. So for those of you who hate integrals and integral equations, you won't have to see them on a day-to-day basis, or at least you won't have to see them every other lecture. The last thing we want to talk about here in chapter 4 is what's called the saddle point method. So this is another method for converting certain types of contour integrals into real integrals that can be dealt with using the Laplace method, or in other words, by applying one of the two Watson's lemmas that we have. So let's jump into it. I think all of the methods that we've had so far have dealt with integrals that have kernels or integrands which look like this. Some exponential portion to the power lambda, where lambda is a large parameter, and then some other function that we have to deal with. Here, this is the same as what we considered, or the same type of integral that we considered in the steepest descent case. So we have h being an analytic function, rho being an analytic function. That means it has a complex derivative, and therefore it has an infinite number of complex derivatives in a certain set. If that's true, then the whole integrand is going to be complex analytic in any set that we choose. So there's no problems there. Well, as long as h and rho are complex analytic on the same set. So we're going to start out with a contour chi, which lives in this nice set D that we're working on. And we want or hope to deform chi into another contour that allows us, as I said before, to convert this integral somehow into one which is amenable to our previous analysis or previous tools from Laplace's method that we learned earlier. So let's make sure I covered everything. So rho is analytic. H is also complex analytic. So recall, in way of definition, we said we're going to break rho up into its real and imaginary parts. And we called the real part phi and the complex part or imaginary part psi. Now, once I remove this complex unit, then both of these functions are real valued. So they take their, they have their domain as D, so they have a complex domain, but the values that they produce are just real numbers. So in the saddle point method, we're going to try to find a new contour that goes through something called a saddle point. And a saddle point of what, you may ask? Well, we're going to find out that it's the saddle point of the function phi. And we're going to travel through a saddle point of the function phi along paths of constant psi. So we want to look for places where psi is a constant or a constant contour. And of course, that means if we're following constant contours of psi, that means we're going to follow undulating terrain for phi. But it just so happens that in this case, we want to go through a saddle point specifically of phi. So here's what we want to do. We have this original contour chi, as before. Now, usually, well, in the two examples that I'm going to give, this complex contour actually is a contour in the real line. So it's a lot simpler than the general case. But in general, chi connects 2 points, z0 and z1 in the complex plane. And we want to make a new contour which connects the same 2 points, but has some nicer properties in some sense. And so that might mean that we create a contour gamma 1 and a gamma 2, a gamma 3, a gamma 4, and then a gamma 5. I've only labeled gamma 1, gamma 3, and gamma 5, because gamma 2 and 4 are going to be what we call bridge contours, and we're generally not going to be too interested in what they do. Okay, so I'll go ahead and just erase those two guys. We follow this contour gamma, which is at its initial, it's just following chi. Then you follow gamma 1, then gamma 2, gamma 3. Let's see, I'll maybe put that somewhere else. Gamma 3, gamma 4, and gamma 5. So ultimately, I create a closed contour, closed loop. And everything is nicely contained in some nice set D. And the whole point of this is kind of a way of deforming the original contour chi, because now I can think about running this part of gamma in the reverse order, and I can get to the same point. So that's what we call a deformation of contour. So I guess I could have made the presentation in either one of two ways. One, the way I did, which is we think about gamma as being some closed contour which extends chi to begin with, or it could have just used this whole concept of contour deformation, which we talked about before. So I chose to do it this way. So we create this closed contour gamma, which does all this and gets us back to the original point. So it's closed, but it basically has the effect of creating or showing us how to create a contour deformation, which is going to be essentially running gamma 5, gamma 4, gamma 3, gamma 2, and gamma 1 in reverse in that order. All right, now we want the same sort of requirements that we had for the steepest descent method to hold again. We want, whenever we run over certain lengths or certain segments of the contour, we want the psi function, which is the imaginary part of rho, to be constant on that contour segment. So for example, on gamma j, we want psi to be equal to a constant cj, and that means it has to be a real constant. It has to be a real value. And this is going to hold for our contours j equals 1, 3, and 5. So this is the typical setup. Now, part 3 or item 3 says psi is not going to be constant on these bridge contour segments, namely here and here, but the idea is we're going to construct those in such a way that whenever we adjust some sort of parameter, it's going to be the same parameter as before, namely r, so that when we send that parameter to infinity, the value of the integral becomes vanishingly small as r goes to infinity. So that's part 4 as well. The other point that I want to mention, or one of the other points I want to mention, is that phi j, or sorry, phi on contour j, where j is equal to 1 and 5. This is a typo here in the notes, and I'll correct it in the slides. This should say j equals 1 and 5. So on these two contours here, here and here, I want phi to be decreasing as I go away from the contour, the initial contour chi. And same here. I want, let me use a different color so that it stands out. So I want phi function, when evaluated on gamma 1, to be decreasing as I move away from chi. And same on gamma 5. As I move away from chi, which is this direction, I want phi to be a decreasing function. Okay, so that's 0.5. 0.6. Now, we didn't say anything about gamma 3 yet. What is phi doing on gamma 3? This is the new part. So along gamma 3, phi has a maximum at some point in the interior of gamma 3 at a saddle point, precisely at a saddle point of phi. All right, so let me show you a picture. So suppose we start off with rho being equal to this function. So rho of z is I times sine of z. I should probably use an equal sign there. Then the real and imaginary parts, I'll show you exactly what those are and how to calculate them in a moment, look like this. So the blue contours are the level curves of phi, the real part of rho. The blue curves are the level curves of phi. And the red curves are the level curves of psi, the imaginary part of rho. So if I look at this diagram, and I'm going to come back to this a few times. So let's look at this point here. This point here is pi over 2. And so it's x equals pi over 2 and y equals 0. That's precisely going to be a saddle point of the function phi. If I look at phi, its contours go like this. If I go in this direction, I'm going up in the value of phi. And if I go in this direction, I'm going up in the value of phi. But if I go in these directions, this way and this way, I go down level curves or down values of I decrease the value of phi. So let's look precisely at this curve here. Let's make it purple so it stands out. So this curve along here, that level curve there, which is a curve of constant phi, goes through a saddle point of the phi function. In retrospect, I think choosing phi and psi was a bad choice. Need something, two functions which sound a lot different from each other, and I'm less likely to stumble upon. Okay, so we're on, with this purple curve, we're on a curve or level curve of constant psi. And it goes through a saddle point of the phi function. And that's because as I go down away from the saddle point, I'm decreasing, and down away from the saddle point, I'm decreasing. But if I go in the perpendicular directions, I'm increasing. So this is a classical saddle point. So let's see if I can draw a good saddle point. Okay. Let's see. Down, roughly speaking. Maybe some of you are better at drawing saddle points than I am. Let's see here. So basically, as we are traveling along this purple curve, basically that purple curve is for us like that. We're going up across through a saddle point of the blue curve. All right, so we'll come back to this in a moment. Why, go ahead.
So on point 6, you say along gamma 3, phi has a maximum at some point in the interior of gamma 3 at a saddle point of it. I just don't understand.
Sure. Okay, so this is going to be my gamma 3.
Yes.
In the interior, I mean somewhere not one of the two endpoints.
Okay.
I'm going to traverse, go through a maximum, and the maximum of that. So you can think about, as I trace out this curve, I'm tracing out the values of a function, right? So down here is very low values of phi. So now I'm going up in phi, up in phi, up in phi, up in phi, and then I reach a saddle point, and then I'm going back down, 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 down. So it's like this, going up, 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 and then back down.
So gamma 3 need to pass through a saddle point in the decreasing direction.
Well, so in the decreasing direction. So suppose I'm running gamma 3 in that direction.
Yes.
Okay. So what I mean is, as I'm going from minus infinity or whatever parameterization, the start of the parameterization, I'm going up, 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 up until I reach a saddle point. Then I'm at a maximum, right? Just as I am here, I'm at a maximum along that curve. And then I go back down, down, down. Does that answer your question?
So for example, if I don't choose this one, I choose
let's say you chose this level curve.
yes.
That one, you're going from a high point down to a low point, back to a high point.
Yeah.
So that wouldn't satisfy what I want.
Okay.
Because we're going through that saddle point at a minimum along that curve.
Okay.
Right? That's a good question. All right, so the reason why I chose to show that plot is because that's related to this integral that we want to solve. So the integral that an integral that we want to approximate for large values of lambda. So let's consider this integral. I of lambda equals 1 over pi, integrating 0 to pi, e to the I lambda sine t dt. Well, this is an integral over a real interval, right? T between 0 and pi. It's a standard integral. Now, this integrand is not real valued, it's complex valued, but I can easily break this into its real and imaginary parts by using the Euler formula. And so this can be easily written as a real integral and an imaginary integral. Now, why am I interested in this? Well, if I take the real part of this integral, then that's just the Bessel function J0. That's the standard definition of the Bessel function J0. It's defined as 1 over pi, integral 0 to pi, e or cosine lambda sine t dt. Okay, that's just the real part. If I take the real part of this, this is exactly what I get. So now if I can understand the asymptotic expansion of this guy, then I can find an asymptotic expansion of that just by disregarding the complex parts. But this original integral, can be regarded as a contour integral in a simple way. So I just formally go in and replace every instance of t with a z, and I replace this limits of integration with integral over chi. So what is this chi? What is this chi contour? Well, it's very simply just the contour which connects the points z equals 0 to z equals pi. So this was a lot like what we had in the previous case. So for the steepest descent, that is the previous example. But I can't use steepest descent methods to analyze this contour for various reasons. They're a little bit hard to explain, but we'll at least explain why the saddle point method does work. Okay. So this is the integral that we want to approximate for large values of gamma, and we want to deform this contour into something which satisfies the previous conditions that I set. Questions? Okay. All right, so we need to understand all we can about the structure of this function, or at least its real and imaginary parts. That's the most important thing. Phi is the real part of I sine z, and psi is the imaginary part. So this, if I'm writing this in by hand, I'm going to write real part, and here I'm going to write imaginary part. This is just the, I think that's math fracture. Is it calligraphic? I think I think it's fractor, but I could be wrong. It's one of the math fonts that is used in LaTeX, and it's commonly used for this is capital I in that font, and so it stands for imaginary part. Now, if I take the sine of z, I can still apply this sine addition formula even in the complex case. It still works. So for example, if I imagine breaking z into its real and imaginary parts as x and y, then I can write z as x plus iy. So sine addition formula still is going to work. We get sine of x cosine iy plus cosine x plus sine iy. It's just that I can easily convert this now into the sinh of y. So sine I of y is just sinh of y, the hyperbolic sine. And cosine, with an I. So sine IY is I times the sinh of Y. So I missed that point. However, cosine IY is just cosh of Y, the hyperbolic cosine of Y. So now just multiply this function by I. That means I'll multiply I here, and this will be I squared. That tells us exactly what a real and imaginary part should be. So in particular, the real part of rho is just minus cosine x sine y. Just this term here with a minus sign because I'm hitting this term with an I. Okay, complex unit. Remember, I squared is -1. And the imaginary part is just this function here, sine x cosh y. So minus cosine x sinh y and sine x cosh y comprise the parts of the real and imaginary functions. And I'm going to continue this abusive notation that I used in the last example, and in the last section, where I'm going to write, even though this, in one way of breaking this down, I want to think of phi as a function of two real variables, x and y. I'm going to commonly think of it as a function of a complex variable, z, where z is a special complex number that has x and y as its real and imaginary parts, respectively. Okay, so this doesn't make sense, right? Because this is a function of a complex variable. This is a function of two real variables, but you can see how to bridge that gap. But it's a slight abusive notation. All right, so the level curves of phi and psi are plotted in the next figure. I've already showed you this. So blue represents the real part. Red are the level curves of the imaginary part. And what we're really interested in here is, where is the saddle point of phi located? Well, remember, we're integrating from 0. So let's put that on here. Our original contour is from here to here. There's 0 and pi. So here's my original contour if I'm going to draw it on there. There's chi. Actually, let's make it straight. Why not? There's chi. Now, remember the methodology. I want to construct gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. What was the requirements? Well, gamma 1, I have to be decreasing in phi as I go along gamma 1. Well, remember, I said before that this is a hill of phi. This is also a hill of phi, and these are two valleys, and they're separated by a saddle point. So which way should I go in order to go downhill? Well, I should go down this direction, because if I go in this direction, I'm going to a hill, an uphill portion of phi. So that tells me what I want gamma 1 to be. I want to go this way. So there's where I'm going for gamma 1. Here's my chi. Now, I need to make a bridge contour because I'm going to have to hop contours. And I can't simply go from one contour to the next without hopping. The next contour I want to go is this guy going through this saddle point of phi. So how am I going to get there? Well, I know I have to go along this contour. So there's the contour I have to take down along there. And I have to continue along this guy. And I'm going to use a symmetric point up here somewhere. So I can't easily draw the symmetric point without drawing this guy. Let's do that. Okay. So now I can connect it. Nope, don't want that. So there's the contour that I want. So this is, gamma 2 is going to be so small it won't show up. So I'm just going to label gamma 3. Gamma 3 is going to go here. Gamma 4 is going to be another bridge contour located up here. I'm going to skip that, skip writing it. And gamma 5 is going to be here. So remember what we said about gamma 5? As I go away from chi along gamma 5, so I have to run it in the reverse direction, I'm going to go downhill in phi. Am I doing that? Yes, because this is a downhill region of phi. These are the two uphills. These are the two downhill directions. Okay. So
Okay, see which one is.
you can't see it from this because I haven't differentiated contours. I've simply written them with the same color. But if you drew the contours with different colors, like a heat map, you would see that this is downhill, that's downhill, and these two directions are going uphill. And another way to see it is just plug in different values. So look at that contour and see what the value is. You'll see, oh, I'm going up, up. Okay.
For the bridge contour, do they need to be on the level set, or do they just be?
The bridge contour should just be as simple as possible. And I think the easiest thing to do is just do a connecting, in the Y direction.
So
But I think you can do it in any direction you want. You can hop contours any way that's
as
easy.
long as they go to infinity, then.
Yeah, right. But the easiest thing to do is I'm going to make this like a minus R value, and up here is going to be plus R value. And then finally, I'm going to send R to be plus off to plus infinity, right? So here's the contour that we want, drawn out in full detail. I did realize, though, I forgot somewhere along the way to actually label gamma 3. So there's gamma 3. I'll need to tell ChatGPT to add that. Where am I stopping? So remember, I want things to be contained in a finite set so that my theory works. This isn't really necessary, and in the end, you'll see that you can skip writing these bridge contours because it's the same story every time. You're basically going to make an argument that the contribution to the contour integration over the bridges becomes vanishingly small. Now I'm stopping down here at minus R, or actually minus Ri, I should say. So I have to figure out, where does this point stop? Well, that's clearly going to be minus Ri in the Y value, or minus R's Y value. Here, it's not so clear what this value is, so I may have to do some calculations to see what it is. I do know, however, that as these guys continue off to infinity, they meet, right? They meet at infinity. They get ever closer to each other. They don't ever equal each other, but they're getting closer as they go to infinity. Questions about this guy? All right, so this is my new closed contour. It's not simple anymore because it's not simple in the technical sense because it crosses itself right here. But that doesn't matter. Okay, doesn't matter. It's still, if I want to do the argument, I can run a subcontour around a smaller one and a subcontour around a smaller one, and just connect the two to each other. On both of them, you're going to find that you have an analytic function, so you're going to integrate to 0, etc. Now I can view this as making this larger contour, which is closed, or as I said before, I can view it as just deforming this contour so that it basically gets you from point Z0 to point Z1 via a different route. But one in this case, which turns out to be a whole lot more profitable and useful for us for doing asymptotic approximations. So in other words, the contour integral along here is the same as the contour integral taken along this direction or along this contour, right? We're just running gamma 5 in reverse and then gamma 4 in reverse, etc. And we get to the same points. So because we're on a set where everything is analytic in sight, the integrals are exactly equal to each other. All right, so let's spell this out in gory detail. So here's the contour segments that we want to compute. These are the ones that depicted already in the figure. Gamma 1 connects the point z equals pi to z equals pi minus IR, where R is a positive number. And it connects it in a straight line. And along that line, that's a level curve of phi. So it's a curve on which phi or psi, sorry. I'm going to keep making that mistake 100 times. It's a level curve of psi. So psi is constant along gamma 1. And we said that phi is decreasing along gamma 1. So check mark, check mark. The bridge contour is going to connect points z equals pi minus I times r to the point z equals xr pi minus ir. I don't know exactly what this point is analytically, but I know that it has to satisfy whenever I put in y for the value, or minus r for the value of y, psi, then this is the value where psi is going to be equal to 1. In other words, this point here, this is a curve where psi is equal to 1. This is a curve where psi is equal to 0. So there's a unique point near this point where this guy transitions from psi equals 0 up to psi equals 1. So whatever that value is, that's what I'm going to call xr subscript pi. Xr subscript pi. And it's a value between pi over 2 and pi. And it turns out it's a unique value. That's the only one that does that. Okay. Now gamma 3 is going to connect xr pi minus ir to z equals xr0 plus ir, where xr0 is this point up here. Or in other words, it's let me say it correctly, xr0 and ir. That's this point right here. And this point here is, I don't know exactly what the analytic value is, don't care. It's xr pi minus ir. Okay, so this is just, I'm saying this analytically. Gamma 3 is just connecting this point to this point and going along that level curve where psi is equal to 1. Okay, psi is equal to 1. Okay, did I say that? Yes, psi is equal to 1 along gamma 3. And as we said, we're going through a saddle point. This is exactly a saddle point of phi. So we're going from a low point up, up, up in phi, up, up, up. And then we cross the saddle point and then we're going down, back down. Okay. So phi is at first decreasing until it reaches the saddle point at z equals pi over 2. And after that, phi is decreasing along gamma 3. And I think it decreases to minus infinity, if I'm not mistaken. So increases up from minus infinity and goes back down to minus infinity. The bridge contour connects this point here to this point here. This point is x equals 0, y equals r, or in other words, z equals r times I. Okay, so connect this point to that point in a straight line shot. And finally, gamma 5 connects the point z equals ir to the point z equals 0, the origin. So go back down. All right, and as I said, everything is satisfied. All the points that we wanted to satisfy with our deformed contour are satisfied. Namely, we're heading in, generally speaking, in the downward direction, that going that way, and the downward direction going that way. That's really all we needed to know. Questions about this before I move on? Okay. So this new curve, gamma, which you start out by running chi, then gamma 1 up to gamma 5, is piecewise smooth. It's non-simple because it crosses itself. That's okay. We know that if we by Cauchy's theorem, if we compute the integral over the closed curve, we get 0. And that tells us that we're allowed to use this part of the curve, running it backwards, as an equivalent contour for this one. Okay, it's what we call a deformed contour. Now, this turned out to be not so fruitful for my analysis, but I still found it interesting enough to keep it in the lecture notes and keep it in the example. So yeah, Calvin.
I think it's go up to √2/2 instead of infinity. The saddle point is.
Oh, the value of the saddle point?
Yeah.
Yeah, the value of the saddle point is finite. The value at the saddle point is not, the value of phi here.
Yeah.
Right? Yeah, it's definitely not infinity. I was saying down here, I think is minus infinity. Going down to minus.
Oh, yeah.
I think. We'll find out better as we do the computation. Okay, so now I want to get an analytic expression for this guy. Okay, or I think my initial thought was it might be useful to have a good expression for that is as a function y in terms of x. Okay, so right, x is usually what we call the real part of z, and y is usually how we label the imaginary part. And I thought, well, it might be nice to have an analytic expression for this guy, probably as a power series, y in terms of x. So how do you get that? Turned out it wasn't so useful a piece of information as I thought initially, but it's still an interesting calculation. If you haven't seen something like this before, it's useful to see. Now, it turns out you can show pretty easily, and what our calculation will show is that the slope of this line as we go through the saddle point, see if I can get a nice, let's use blue. As I go, no, that's gonna be horrible. But I can adjust it, right? No. Iteratively. So that looks pretty good. The slope of that line going through that saddle point, okay, y is a function of x, is just 1, actually. So basically, I can approximate this as being this part very close to the saddle point as being a linear function y in terms of x or t, whatever, with a slope which is exactly 1. So I want to at least show you that. But actually, what I attempted to do, I accomplished quite nicely, is I found a power series expansion of this function y in terms of x. So I want to show you that. In fact, I converted it to t, which I'll show you in a moment. Let me show you how to do that because it's actually kind of cool. All right, so I want to get an expression of y, I want to find a function y in terms of x so that it's exactly this contour. Psi equals 1, going through that particular saddle point that I pointed out, which is has the value x equals pi over 2. So how do you do this? How do you start with a relation like this and come up with an expression like that? Now, first of all, note that, let me go back here. This function here, this curve here, is also psi equals 1. Okay? This is psi equals 1. This is psi equals 1. And that makes sense, right? They cross each other. They cross each other through the saddle point of phi. So when I compute this guy, using that expression, the expression that I want to use is this one. I get a non-unique curve because through the saddle point, this curve is like coming up and going like that, but it also has another branch which goes like that. So how do I know which one I'm getting on? Well, I know that I know that the correct one by the geometry has to have a negative slope if I write y as a function of x. I don't want this guy, in other words, I want that guy. right? So, but you can see that through this point, there's a non-unique description of that curve, right? Through this point, I could either take that branch or take that branch, and they're not equivalent to each other. Now, if I'm talking about going through this point, there's only one psi equals one curve which goes through that point. It's just certain points you have non-uniqueness, okay? Namely at saddle points, actually. All right, so as I said, there are an infinite number of curves. Actually, there are an infinite number of curves that have the expression psi equals 1. There are exactly 2 which cross and go through this saddle point. But there are an infinite number of curves where this happens for this particular function because it's a periodic function. So there's a psi equals 1 curve. Here's a psi equals 1 curve. Here's a psi equals 1, psi equals 1, psi equals 1. And it just repeats off to infinity in both directions, okay? So there's a lot of non-uniqueness around, but we can get uniqueness once we specify exactly which branch we want to follow. So there are 2 such curves which pass in the domain x equals 0 up to pi, both of which pass through the saddle point at z equals pi over 2, or in other words, x equals pi over 2, y equals 0. The above relation can be changed slightly. So we just can recognize that let's divide both sides by the cosh, and we can get the hyperbolic secant on one side, right, by dividing by the cosh. And on the right-hand side, we still have the sine, but I'm going to write sine in a slightly different way because I know that, well, my coordinate system would be a lot easier if this was the 0 coordinate here. So I'm going to do a slight change of coordinates and set t equals to x minus pi over 2. Okay, so that coordinate system starts right here, right? So whenever x is equal to pi over 2, t is equal to 0. So that's what that change of variables is doing. And so once I divide by cosh, I get hyperbolic secant on the one side, sine x on the right-hand side, but I'm going to replace the x with t plus pi over 2. All right? So let's see what this does for us. Now, it turns out that we actually have power series expansions for y, and of course, for the hyperbolic secant in terms of y. And we can also generate very easily a power series expansion for the sine function in terms of t, right? No problem there. So what are these power series expansions? Really cool. I tracked these down. I've seen them before, but I haven't seen them in a while. But the power series expansion for the hyperbolic secant, 1 over the cosh, is this power series expansion here. It only has even terms of y, which is kind of interesting. And it's given in terms of these things called the Euler numbers, okay? EK in particular is the kth Euler number. We only need the even ones, okay? In fact, maybe there only are even ones of the Euler number. I forgot. Right. And so 1 over that is going to be even as well. So it makes sense that it should only be in even powers. So E0 is 1, E2 is -1, 4 is 5, 6, and so on. Okay. The signs alternate. There's no, let's see, I'm not sure there's an analytic expression for what these values are, but they're computable to any order. There's recursion relations for computing them. These are the Euler numbers. You may have seen Euler numbers in conjunction with things called the Bernoulli numbers. Has anyone seen these before? Okay. So I'm not going to derive them here, but this is a kind of interesting expansion. The sine of t plus pi, I'm going to expand around the point t equals 0. So in Maclaurin expansion, same here, right? Around y equals 0. By the way, this power series expansion of secant, hyperbolic secant in terms of y, has a radius of convergence of only y between -pi over 2 and +pi over 2. In fact, I need to check this. This might not be the equal sign here. This maybe should just be a less than.
Because it should do infinity.
Well, not just because of that, but it's a little more restrictive even than that, actually. So it doesn't quite fit the full, right? So hyperbolic, let's see. So this one, let's think about this for a second. So what is the hyperbolic cosine look like? It's a cup, right? Right. And so what's the reciprocal? What's the reciprocal look like? Should be something like this, right? So what it's saying, all it's saying is you can get a power series expansion, but it's only valid for small range. Okay. But that's not actually going to be a problem for us. It turns out the calculations we're going to, so by the way, the range here is minus pi over 2 to pi over 2. The calculation I'm going to do, I believe, is going to work for all the values of x that I'm interested in, which is quite nice. All right, so the sign of t plus pi over 2 is this power series expansion. You can just modify the original or the standard sine function power series and get this. By the way, what does a sine function look at t plus pi over 2? Well, sine looks like this, right? So we're going like that, right? And so here's x. No, let's see. What am I saying here? This is x, right? So my t coordinates are here. So this is pi over 2. So basically, this function is also an even function, right? Well, it doesn't go down forever, but you get the idea. So sine is not an even function, but if we shift it so that its center is around pi over 2, then it becomes an even function again. So the expansion of this is only in even powers of t. Does that make sense to everybody? See sine as an even function around pi.
I mean, they're just cosine.
Yeah, right. That's right. Now I have two power series that equal each other. One's a crummy power series in y, and the other one's a crummy power series in t, right? Well, for small values of y and t at leading order, we're going to say, well, y squared is probably just equal to t squared because both are small at the same time, right? Whenever t is small, y is small, correct? Because t is small, y is small, that means here's t axis and here's the y axis. So whenever t is small, y is also small, right? So it stands to reason that for small values of y and t, here's our leading order approximation. All right, so to traverse this in the correct direction, what we really want is, let's take the square root of both of these. So we either have y as to leading order going to be t, or y is the leading order minus t. Well, we already know what the correct one should be. We want the negative slope. So y to leading order should be minus t plus order t squared. Does that make sense to everybody? And it looks like it's true from the picture. You have a slope of basically -1. So this will help us develop the power series expansion of y in terms of t, which is what we want. I thought it would help me do a lot of nice analysis in the saddle point method. Turns out it's of limited use, but still cool, right? So so from this point on, you can shut your brain off because it's not necessarily germane to the topic that we have. But the question is so this gives me my leading order, right? How could I come up with a power series expansion of y in terms of t, just knowing this information and this leading order information? Well, what I'm going to do is I'm going to proclaim that there's a power series expansion out there which has this expansion. And the leading order I'm going to choose to be minus t because that's the correct leading order. Okay, for t small, y is also small. We should just have y approximately equal to minus t. So this y star is the power series expansion that I'm seeking. The problem is I don't know these coefficients, C3, C5, C7, C9, C11. Now, I know that this y function, or at least it looks like it should be, this y function should be an odd function in terms of t. Okay, so I'm also positing that that's true. However, I think I can prove it's true without too much trouble. That also makes sense from the thing I've drawn here. Like if I set my coordinate axis here to be t to start here, then y should be an even or an odd function of t. Okay, when I square it, I get an even function of t, correct? You look puzzled, Calvin. Any questions?
No.
Okay, good. So everybody's okay. We have this odd function. Now we just want to figure out what are the coefficients C3 up to all these odd coefficients, right? Originally, when I did this, I put in the even coefficients as well, and I was getting 0 for every even one, and I realized, oh, that's the stupid mistake I made. Okay, so now what should I do? I have this relation. Remember, this is the original relation I had. Okay. Equating the two power series, the one for the hyperbolic secant and the one for the sine. Okay. So now let's just pretend like this is a polynomial and dump each one of those expansions in here and expand out term for term. Okay. This can be done, right? Did somebody say no?
You're doing the homework.
Yeah, right. So if I'm only matching, remember, if I plug in this power series here and I square it, then I know I'm only going to turn up certain powers, and I'm going to start by equating powers. Same here. I'm going to take the power series expansion for y, and I'm going to take it to the 4th power, and then I'm going to get a power series. Take it to the 6th power, I get a power series, etc. And then I'm going to start by equating coefficients. I'll have a power series at the end of the day in t over here, and I have one in t over here already. So let's see what we get. If you do this sort of construction, so I plug in this value of y and I square it. I take that power series into here, take it to the 4th power, take it to the 6th power, and all the terms of like. And then I start equating coefficients, and here's what you get. C3 has to be minus 1/6. C5 has to be minus 1 over 24. C7 has to be this number, and C9. They all turned out to be negative, interestingly, which is kind of makes sense to me, but that's a different story. So now as t goes to 0, I get this power series expansion. Okay, around the Maclaurin series for y star in terms of t is just this odd function here. And I kept going because I was kind of interested in this. And it turns out I could actually come up, at least with all the values that I computed to all orders that I could compute by hand. No, I threw this in Mathematica. I threw it in Mathematica and I found out that at least to all orders I could compute, I get these Euler numbers popping back out. So I get a nice analytic expression for this power series. Okay. I plotted it out to like the 9th or 10th order. It matched the contour that I could compute in math. Did I say Mathematica? Yeah. In Mathematica, it overlaid it precisely. So this was kind of a cool computation. And I thought, this is going to be great because this is going to help me solve my problem. Turns out I never actually used that. I never actually used it, but it's cool nonetheless.
I think I have a way better solution.
Oh, great.
Can you swipe to the first line, like about the sine code?
Right here?
No, really, early.
Yeah.
In this one. I think what you can do is you can throw the sign to the right hand side.
Yes.
And you know that you are doing it on sine pi over 2.
Yeah.
Which is around that point, sine is like nearly 1 but slower than
Yeah.
less than 1. So 1 over sine is greater than 1.
Okay.
Right? So now for the cos, you have the 2 branches here.
Uh-huh.
And when you do the inversion, do the final inverse, you have 2 branches. One is greater than 1, one is smaller than 1.
Okay.
And we know that this should be the one that is greater than 1. So actually, you divide sine to the right hand side, you can actually just apply the inverse formula for cosine, hyperbolic cosine, which take the equal direction.
That's true, but I really wanted a power series because I thought I was going to have to integrate term by term. Okay. So I knew, for example, at this point here, I could just take the inverse hyperbolic secant.
Yeah.
And that's a nice function, actually. It turns out it's tabulated in Mathematica. And I could just say y is equal to the inverse hyperbolic secant of blah, blah, blah.
Mhm.
And I plotted it and it worked.
Okay.
It was something. Okay.
So you check with that answer.
Yeah.
Okay.
Yeah. But the point was, okay, so now you have inverse hyperbolic secant. What's the power series or functional? Then I thought, well, you know how sometimes you can do things like if I have the secant, if it's just the secant inverse of the sine, then there's a nice formula for that, right? There's little tricks for computing those values. Or the inverse cosine of the sine is blah, 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 right? Has some sort of rational, it's actually equal to a rational polynomial, right? Or something maybe with a square root, okay? Radical rational, something like this. So I couldn't do the same thing here because this was not the secant, this was the hyperbolic secant inverse function. Yeah. I played around with it for a very long time until I came up with this, and then maybe after a week of playing with it, I realized it's not going to be useful anyway. So, oh well. All right, so now the integrals over gamma 1 and gamma 5, these integrals turn out to be purely imaginary, okay? So you can do them. I'm going to leave the details for the interested reader, maybe a future homework hint. That these, you can evaluate these integrals, either exactly or approximate them, but the integrals themselves turn out to be purely imaginary. And so at the end of the day, I'm going to take the real part of everything. So as long as these are just finite, I don't care. I'm going to take the real part, and these guys don't even appear in the real part, right? Because they're purely imaginary. Why am I taking the real part at the end of the day? I'm sorry to swipe back so much, but the integral that I want to compute is this guy here, right? Actually, the way I have it written, I really do want those guys, but I'm really just interested in an expansion for the Bessel function. Now you remember that before we used a method to get a one-term approximation of the Bessel function. We used the method of stationary phase. Method of stationary phase, generally speaking, at best only gives one-term approximations. And so the saddle point method is going to give us approximation, an asymptotic series expansion to any order that we want. And so that's one advantage of using it. Okay, so we want to get out of that though. Now, the bridge contours, gamma 1, gamma 2, and gamma 4, same or similar story as before. We're going to take r to infinity, and it turns out that these integrals go to 0 as r goes to infinity. So they're controllable. They're well behaved as r goes to infinity. Okay, they don't go to like 5 or 6 or minus 10 times I. They just go to 0. So that's great. Otherwise, we just would want them to be, as r goes to infinity, maybe you just converge to a number. But here it's the best number, right? 0. I don't have to consider them at all. It's the gamma 3 contour that is the real son of a gun, okay? That's the one that we have to work really hard on. So remember on gamma 3, psi has the value 1. So remember, we're on psi equals 0 contour, then we jump over to psi 1 contour, and we jump back to a psi 0 contour. I may have failed to say that, but the gamma 5 contour is a psi equals 0 contour. Gamma 3 contour is a psi equals 1 contour. And it satisfies all the nice properties that we want. Phi along gamma 3 as we traverse it is at first increasing. Then we go over the saddle point. It has a value 0 at the saddle point. Calvin, I think you said, what did you say the value you thought of phi was?
1, I think.
You think it should be 1?
Yeah. Wait a minute.
Well, let's see. So all we have to do is what was it? So phi was equal to minus, what was phi? If I say what it is, it'll be wrong. So I better go look. Minus cosine x sinh y. So sinh of y is 0. That's the thing.
Okay.
When I put in y equals 0, I get 0. Right? Okay, so that's okay. This should be 0. All right, then it's decreasing along gamma 3 after I pass through the saddle point. And we're going to take the limit as r goes to infinity ultimately, so let's take it now, might as well. Okay. Suppose that a parameterization of gamma 3, now gamma 3 is an infinite in extent contour because there's no bridge contour anymore, right? It goes all the way down to, it goes all the way up through the saddle point and all the way down, and it has vertical asymptotes, right? At x equals 0 and x equals pi, it has vertical asymptotes. But suppose that I have some parameterization for gamma 3. Now I'm running gamma 3, actually I run gamma 3 this way up to that way. So I'm going to parameterize it from minus a to, actually it doesn't matter how I parameterize. I'm going to parameterize from minus a to a plus a, but I'm running it in this direction. And I'm going to make it even, the parameterization, so that when I run through 0, I'm crossing through pi over 2. Does that make sense? I'm crossing through the value. So this is a complex number. So this is complex value pi over 2. So that what I mean is it has the real part pi over 2 and imaginary part 0. Okay, so remember how we define contour integration. You have to, when you integrate over gamma 3, you're going to, let's see. So the first thing I'm going to do is break rho into its real and imaginary parts, fine. The next thing I'm going to do is evaluate z at gamma 3, and to compute this contour integral, I'm going to compute the integral from t equals minus a to plus a. The contour is going to run over z equals gamma 3, and then I have to multiply by gamma 3 prime. Now, what happened to the imaginary part? Well, remember, on gamma 3, psi is exactly equal to 0. No, that's not right. It's 1. It's 1. So I was wondering, where did it go? It actually popped out front. Okay, so it's e to the I lambda. So that's this part. Psi is equal to exactly 1. So that guy can come out. It no longer depends on z. This part here, this is a function which has a maximum at t equals 0, right? Goes up, has a maximum at t equals 0, and then goes back down. Okay, whatever it is, I don't care. I parameterized my curve in an even sort of sense so that I can now replace this integral from minus a to a with an integral 2 times the integral from 0 to a, right? That's because I parameterized it sort of equally on both sides. And I know also that phi has a symmetry on both sides of that curve as well. Okay. So it's a symmetry argument, which allows you to replace this integral with 2 times the integral from 0 to plus a. Questions? Okay. Now we're going to make a change of variable, which is basically analogous to the change of variable we made in the steepest descent case. And we observe something, namely that along gamma 3, so along gamma 3, I know something. So rho run along gamma 3 is going to give me an imaginary part, which is just 1. So that's I. And a real part, which is just going to be, I guess I have it written out here. I don't know why I'm rewriting it. Yeah, it's just right here, right? This part here is my real part, and my imaginary part is just 1, has size 1. Now this is what is this? This is a real function, right? And now it's a real function of a real variable. Okay, real function of a real variable. And what happens? It goes from minus infinity up to 0 and then back down to minus infinity. All right, so it's kind of like what does that shape look like? It looks a bit like that. So as t goes along, phi, when I run along gamma 3, goes up to 0 and then back down. Okay, so that's like a parabola, right? So I could replace this by something which looked like a new variable, and I could call that new variable, let's say, r squared. Or I can transform this negative parabola into a linear value. And the reason is because I'm only evaluating it from 0 to, for positive values of t. So I can kind of think about this. I could make it minus r squared something, or I could just make it minus r. Either way, it still works. Okay, so I have this because I'm ultimately going to do a change of variables. That's where I'm going with this. So the change of variables I'm going to introduce is going to be q of t. Let's see. Q of t equals minus phi. Why minus phi? Well, I know that it's going to be, I know that this guy is going to be a negative number, so I'm going to convert it into a positive number, okay? So the new variable is going to be q, the old variable was t. The new integration variable is going to be q. So let's solve for minus phi of gamma 3 of t. So to do that, I just move everything to the other side, right? So I move this guy over, and then I move this guy over. So I get I minus I sine gamma 3 of t, correct? So q is a non-negative real number because this was non-positive, right? This guy phi was non-positive. It goes like this. But if I put a minus sign in front of it, I flip it to the upper side. Okay, so my q variable is going to be something which looks like this now. All right, so now let's take, whenever you do a change of variables, you have to take the derivative with respect to the old variable. So I'm going to need to replace dt with dq, right? All right, so I'm going to take dq dt and see what I get. dq dt is equal to minus I cosine gamma 3 t gamma 3 t prime. All right, now this turns out to have a very nice structure because I'm getting a gamma 3 prime of t out, which is what I want. I'm going to move the dt over and hug this gamma 3 prime of t, right? Notice that my integration, that's exactly what I want to replace. So that's why I'm doing this trick this way. Problem is now I get what? I get this I cosine in the basement, and I might not be able to deal well with that. It's not so bad though, as it turns out. Now I need to change limits, right? So whenever t is equal to 0, t is equal to 0, q turns out to be 0 as well. Okay, so that gives me my lower limit for q. What about for the upper limit? Whenever t is equal to a, this thing goes down to minus infinity. So if I throw a minus sign in front of it, it's going up to plus infinity. So q is now a variable which is going from 0 to plus infinity. from my variable phi, if you want, or from my variable t, which was going to 0 to a. Okay, so now here's my new integral that I have to compute. So I still have to take care of this cosine thing. Well, it still holds true in complex world that cosine squared plus sine squared is equal to 1. So cosine squared is equal to this. Now, if I take the square, if I just blindly take the square root of this, I could get in trouble because I have to choose either the plus square root or the minus square root. Now, sine squared of gamma 3, what is that? That's the thing I need here. I'm going to solve back in terms of q. Remember, sine gamma 3 of t can be written in terms of q. If I square it, I'm going to just get this, 1 plus 2i qt minus qt squared. Okay, that's just using this change of variables relationship that I have. Therefore, I can compute the cosine squared, no problem, in terms of just the q variable. This is starting to look really nice because now I can replace this with just stuff involving q. All right, but the problem is I need to take a square root. Which sign should I take for this square root, and will it make sense? Turns out it makes sense, no problem. But I have to take the minus sign. And the reason is if I take the plus sign, I get the wrong answer, period. Okay, you get negative the answer. The way I knew this is because if you take this out to its conclusion, you'll find an approximation for the Bessel function. And if it has the wrong sign at leading order, then you know it was the wrong sign. And that's how I figured it out. Has to be the minus sign. Okay, so minus the square root of q squared. Remember, I'm taking, I'm subbing in now. Sine is this, but I take 1 minus that, right? So there's my cosine. Take the square root of that, get that, and I choose the minus square root. And then I do a little bit of work on this. I'm going to pull out the factor of minus 2i q, and that leaves all this business left inside in the square root. I haven't really done anything yet. Still have my minus sign out in front. I'm going to get a minus square root of q, no problem there. I also have a square root of 2, but then I also have a minus I with a square root. What the heck does that become? Well, it turns out you can show that that becomes I times, it involves a slight little complex analysis, not complex analysis, just you're just using polar coordinates, really. That just comes out to minus I square root of 2 e to the I pi over 4. Okay. All right, so what haven't I said? So blah blah blah. I think we're okay. Oh, the other thing I did here is if you divide by I, that's the same as multiplying by a minus I. So that changes the sign of this guy to plus I qt over 2. But now look what has happened. This is now totally in terms of q. So I can totally convert to my q variable. But it's a hellacious nightmare of an integral, right? You get that. What can I do with that? Well, remember, we're doing Laplace's method, and we're going to use Watson's lemma. The integral that I have to calculate is integral of 0 to infinity e to the minus something, a bunch of other stuff. This guy doesn't look nice, but I could get a power series expansion for that. And remember what Watson's lemma says, that if I can get a power series expansion for something which looks like this, no matter what it is or no matter what the radius of convergence is, I'm still going to get an asymptotic series out of it. Doesn't matter what the radius of convergence is. Even though this is integrating from 0 to infinity, and I might be able to get something with a radius of convergence maybe like 1. No problem. Okay, no problem there. Okay, so this is the integral that I want to compute. I'm going to bring this stuff out front. See, that all comes out as this business here. Okay, no problem. 2 over square root of 2 gives square root of 2. So I have to compute this integral here. How do I do it? I'm going to use Watson's lemma once again. So I need the power series expansion for something which looks like this. This time I got it right. Actually, if you looked at the previous version, I had some crazy stuff going on. This works for any Z, so I can put in my Q over 2 here and I get this power series expansion. So I'm in plus time, but if you give me a minute, I will finish up. So my Watson's lemma says that I can replace this with its power series expansion, integrate term by term, and I get an asymptotic series approximation. So that's exactly what I do. This is Watson's lemma here. I'm subbing in this power series expansion, and I'm going to integrate term by term now. And now I'm only in the Q variable. Okay. Well, now you can throw this into Mathematica. Mathematica says no problem, can do it. And you get this integral out, this result, gamma k plus 1 over lambda k plus a half. Okay, no problem here for doing these integrals like this. All right, so now that gives us our power series, asymptotic power series expansion in terms of half integer values of k, no problem. All right, so now I have to complete the story. So we needed I lambda, and I lambda was all that. Okay, so we said that that's going to be minus I1, minus I5, minus I3. We just run the gamma 1, gamma 3, and gamma 5 contours in reverse, and we can replace that original contour integral with those contours. But I1 and I5 are purely imaginary. So ultimately, at the end of the day, I'm going to take the real part of that to get the Bessel function. So when I take the real part of that, these guys don't contribute, and I only get the real part of that. But notice this has a minus sign in front of it. This has a minus sign in front of it. I needed that extra minus sign to cancel, and that's why I chose the minus sign in the in this analysis here. Why I chose that minus sign, because you get precisely the right answer with the wrong sign if you do it otherwise. All right, so at the end of the day, let me boil this thing down so that we can leave here happy that we have completed this chapter. If I want to compute the Bessel function, I take the real part. I'm going to do that. Then I'm going to multiply, or I'm going to figure out what this power series says term by term. It's ugly, but it's not hard. You take the real part of that, etc. And I can do this for an infinite series. I'm only going to truncate to 2 terms though. I'm only going to get the term that I had before. This is the term that we computed as the Bessel function approximation using the method of stationary phase. And this is the next term that we get from the asymptotic expansion that we just did using steepest descent. Now we can get an infinite number of terms. I've only wanted the second correction for this. And the second correction is precisely this. I didn't plot it. That would be nice to throw a plot in the book and maybe in the slides to see how much more accurate that this 2-term approximation is than the 1-term approximation. But if you go back to the method of stationary phase, this 1-term approximation was already quite good approximation for large values of lambda for the Bessel function. So adding this in should make it even better. All right. So I'm sorry for taking extra of your time, but I'll give it back to you someday, maybe. And have a nice break. We won't have class on Thursday. I hope you all know that. Or if you're learning it now, I hope you enjoy that piece of information. I will be over the break, I will be posting the homework solution. So you're probably wondering where that is at and what is the story with that. I'll be posting those, and I'm going to tell you my interesting grading scheme that I think you'll all really like. Okay, interesting grading scheme which you'll all really like. So it's good news all the way around, and most of it. But I'll post those solutions, and I'll see you guys 1 week from today, Tuesday.